Welcome to this explainer. So today, we're diving into something really fascinating. We're talking about the unsung, money-saving heroes of modern chemistry, catalysts. Seriously, if you've ever wondered how these massive global industries manage to pump out mountains of chemicals without just completely bankrupting themselves on energy bills, well, you're exactly in the right place. All right, let's take a quick look at our roadmap for today. We're going to start by pinning down exactly what a catalyst is, then we'll run through their strict rules of engagement, check out some heavyweight industrial examples, unpack why they matter so much to the global economy, and then wrap the whole thing up with a rapid-fire exam revision session. Okay, section 1. Let's start with the most obvious question. What exactly is a catalyst? By definition, a catalyst is a substance that increases the rate of a chemical reaction without being used up or permanently changed. And I really want to emphasize that reusable nature because it's key. Think of a catalyst as the ultimate instigator, right? It speeds up all the chemical drama, it gets all the other molecules reacting way faster, but it absolutely refuses to get permanently involved itself. It goes in, does its job, and comes out looking exactly the same, totally ready to just do it all over again. So how does it actually pull this off? Well, it provides an alternative reaction pathway with a lower activation energy. It's basically a shortcut. Imagine you're trying to get to the other side of this massive mountain. Without a catalyst, you've got to hike all the way up and over the peak. And man, that takes a ton of time and a huge amount of energy. Adding a catalyst is literally like finding a hidden, low-energy tunnel straight through the mountain. You're still going to the exact same destination, but it requires way less energy and you get there a heck of a lot faster. Moving right along to section 2, the rules of catalysts. Here are the non-negotiable rules. What a catalyst does is speed up the reaction and lower that activation energy. It opens up that mountain tunnel. But crucially, here is what it does not do. It doesn't get used up, it doesn't change the final amount of product you get, and it doesn't change the position of equilibrium. It only helps the reaction reach that equilibrium faster. Basically, catalysts get you to the finish line in record time, but they do not change your final destination or the amount of stuff you create. You don't get more stuff, you just get it sooner. All right, section 3. Let's look at some heavyweight industrial examples you definitely need to know. Think of this as your ultimate cheat sheet. So first, for the decomposition of hydrogen peroxide, we use manganese 4 oxide. Next up, the Haber process. That's the manufacture of ammonia. For this one, the catalyst is just iron. Then there's the manufacture of sulfuric acid, known as the contact process, which uses vanadium 5 oxide. And finally, the hydrogenation of vegetable oils relies on nickel. Now, I want to specifically highlight iron for the Haber process and vanadium 5 oxide for the contact process. Seriously, burn those two into your brain. They are super common test questions and literal pillars of global industry. Which brings us to section 4, why catalysts actually matter in the real world. This is where we connect the chemistry lab directly to the global economy. See, by lowering that activation energy, reactions can happen at much lower temperatures, and that means you need less heat. Generating heat on a massive industrial scale, yeah, that is incredibly expensive. So less heat equals a massive reduction in energy costs. Plus, it makes the whole process vastly faster, skyrocketing your overall efficiency. In business, saving time and saving energy means saving ridiculous amounts of money. Catalysts are quite literally the financial backbone of chemical manufacturing. Okay, section 5. Time to lock this in with some quick exam revision. Let's run a rapid-fire boot camp. Try to guess the answers before I reveal them. Ready?
Question 1. What is a catalyst and how does it speed up a reaction? I'll give you a second. Try to picture that mountain tunnel analogy we talked about.
And there it is. A catalyst increases the rate of reaction without being used up by providing an alternative pathway with a lower activation energy. It is so absolutely vital to hit those specific keywords on an exam without being used up, alternative pathway, and lower activation energy. Nailing those terms will guarantee you full marks.
All right, next question. And watch out because this is a classic trick question. Does a catalyst change the amount of product formed? Think back to those rules of engagement.
The answer is a hard no. It only changes how quickly the reaction reaches completion or equilibrium. Let me say that one more time just to be safe. The final output amount remains exactly the same. The catalyst isn't magic. It doesn't just spawn extra product. You just arrive at the end of the reaction much, much faster. Okay, final test question. Name the precise catalysts used in the Haber process and the contact process. I challenged you to memorize these earlier. The two heavyweight examples. Do you remember them? Let's see if you got them. For the Haber process, the catalyst is iron, and for the contact process, it's vanadium 5 oxide. It's actually kind of brilliant when you think about it. How simple elements like iron and specific compounds like vanadium 5 oxide are the true unsung heroes behind the manufacturing that keeps our modern world running. To sum up this entire explainer, if you remember literally nothing else today, remember this core formula. Catalyst equals faster reaction plus not used up. Seriously, drill that into your memory. They speed things up and they live to fight another day.
I'll leave you with this thought. With catalysts saving the world so much time, energy, and money every single day, what other incredible chemical shortcuts are just sitting out there, waiting to be discovered in a lab somewhere? Thank you so much for joining me for this explainer today. Keep exploring, study hard, and as always, stay curious about the chemical world around you.